This week, we're going to begin to explore the biogeochemistry of wetland ecosystems. In the first part of this unit, we will explore components of the carbon cycle in wetland ecosystems, including primary production, herbivory, and decomposition. We will also examine the importance of wetlands in the global carbon cycle. In the second part of this lesson, we will introduce some of the unique chemical conditions and microbial reactions that occur in wetland soils. And we will learn the role that wetlands play in terms of emitting, removing, or storing materials as they pass through the landscape. So this is a summary of the carbon cycle in wetland ecosystems. We're going to walk through all of these processes one at a time, but the first thing I want to emphasize is that there is one major source of carbon to wetlands: plant photosynthesis, or primary production. So we're going to start there. This is a simplified view of the carbon cycle, or how an ecosystem ecologist views the carbon cycle. There are three major reservoirs: CO2 in the atmosphere, organic carbon in the soil, and plant present in living biomass. Biomass is a reservoir composed of all living organic matter. Detrital organic matter, or dead organic matter that has not decomposed, is typically included in a separate reservoir or in the soil reservoir. Gross primary production represents the transformation of atmospheric carbon dioxide into organic carbon. This transformation links the atmosphere to the wetland ecosystem. Plants also perform cellular respiration, just like we do. Plants will burn some portion of the organic carbon that they synthesize to perform regular cellular maintenance. This organic carbon does not stay in the biomass reservoir. That is, it does not show up as new plant growth. Respiration returns carbon back to the atmosphere as CO2. Respiration occurs in all tissues of the plants, including leaves and stems, but also non-photosynthetic tissues like roots and rhizomes. These two processes, both performed by plants, dominate the carbon cycle in terrestrial and most wetland ecosystems. We can express the net amount of photosynthesis, or the amount of carbon left over for plant growth after losses due to respiration, as net primary production. This is analogous to your net salary after deductions from your gross income, like Social Security and taxes and whatever. Net primary production represents the rate of new production of plant biomass over time. It is equal to the rate of gross primary production minus the rate of plant respiration. There are two major strategies for quantifying primary production. The first is that we can harvest plants after a certain period of time, or measure how quickly they accumulate biomass over time, to measure the rate of new production of organic carbon in the biomass reservoir. This method takes a bit longer, especially depending on how quickly the plants grow, and the harvest method is also destructive. The other strategy is to measure the rate of production of products of photosynthesis and respiration, like CO2 or oxygen. For terrestrial plants, it's relatively easy to measure the rates of production and consumption of CO2 over time. In this photo, I'm using a liquor, or a gas exchange analyzer, to measure the exchange of CO2 across a small area of plant leaf. This measurement can be completed in less than a minute for most plants. If you measure the uptake of CO2 under full light conditions, you are simultaneously measuring GPP, or the gross photosynthetic rate, and plant respiration at the same time. In other words, the plant is performing both of these processes inside the leaf chamber under full light. So what you are directly measuring here is NPP, or net primary production. If I wanted to determine the plant respiration rate, I could simply deprive the plant of light for a period of time until it stops photosynthesizing. I could repeat the measurement on the plant, which is now respiring but not photosynthesizing. If I wanted to determine GPP, or gross primary production, I could now calculate it using those two measurements. I would take my estimate of NPP from the light measurement and add in the carbon lost to respiration in my dark measurement. This would tell me the total amount of photosynthesis that the plant is doing, or gross primary production. You can perform a similar measurement for submerged plants, or algae. In water, it's easier to measure oxygen than carbon dioxide, so that is typically the measurement that we use. We can put a known mass of plant in a light bottle or a clear bottle, pictured here on the right, and measure the rate of production of oxygen over time. Again, the plant is performing both photosynthesis and respiration in the bottle. So measuring the production of oxygen in the light bottle will provide us with an estimate of NPP, or net primary production. We can also put a known amount of plant inside a dark bottle where the plant will perform respiration but will be unable to photosynthesize due to light limitation. Measuring the rate of consumption of oxygen in this bottle will provide us with an estimate of plant respiration. If we wish to calculate GPP, or the gross primary production rate, we can add the losses due to respiration, which we measured in the dark bottle, back to our estimate of NPP, which we measured in the light bottle. When you are performing these calculations, it's worth remembering that your estimate for GPP should always be greater than your estimate for NPP. I emphasize that the two largest transformations in the carbon cycle are typically performed by plants. But what about other things in the ecosystem that are not plants? Other components of the ecosystem can also remove organic carbon from the ecosystem, either back to the atmosphere as CO2 or due to losses downstream. The other major losses include respiration by heterotrophs, including consumers and detritivores, or decomposers, losses to disturbance, including burning, harvesting, or filling, or losses due to leaching. I use losses due to leaching from tea leaves to make this delicious, delicious dissolved organic carbon just a little while ago. Delicious dissolved organic carbon. Once all of these other losses are taken into account, we can compute a term called ecosystem production, or NEP. This is equal to net primary production minus all of these other losses of organic carbon from the ecosystem. These other terms appear here on the carbon cycle. Notice the relative difference in size between these losses and losses due to plant respiration. NEP takes into account all of the ways that organic carbon can be lost from the ecosystem, in addition to plant respiration. If this term is positive, if NEP is positive, it tells you that the ecosystem is accumulating organic carbon in the ecosystem over time. If it is negative, it tells you that the ecosystem is losing organic carbon over time. NEP is typically measured using eddy flux towers to measure the net exchange of CO2 between the atmosphere and the biosphere over time. The tower is placed downwind of the ecosystem at a height above the canopy. The eddy diffusion approach does not directly measure NEP. Instead, it measures a similar term called net ecosystem exchange, or NEE. This is a picture of an eddy flux tower that has been installed over a coastal marsh. There are a couple important differences between NEE, or net ecosystem exchange, and NEP, or net ecosystem production. The first is that NEE refers to the amount of CO2 in the atmosphere. So it will be negative if the ecosystem is taking up carbon and carbon is being lost from the atmosphere over time. And NEE will be positive if the ecosystem is losing carbon to the atmosphere or the atmosphere is gaining carbon over time. Therefore, when NEE is positive, that means NEP is negative and vice versa. The second difference is that it does not directly measure losses of carbon to downstream ecosystem or leaching. This term shows up as part of the CO2 that's absorbed by the ecosystem. This term is typically small, so usually we don't have to worry about it. But as we will see later, wetlands export a lot of dissolved organic carbon. If we wish to measure that term, we would need to collect additional measurements of export of dissolved organic carbon to groundwater. Second, eddy flux towers do not typically capture disturbance events. You would need to know that a disturbance is going to occur and install an eddy flux tower in advance of the event and have it running and calibrated when the disturbance occurs. And this almost never happens. So these measurements typically do not include losses due to disturbance events. So to sum up, NEE tends to be more negative if there's a greater flux of CO2 leaving the atmosphere. And this could be due to increases in carbon stored in plant biomass or in soil organic carbon, but it could also be due to leaching of carbon from the ecosystem to groundwater. NEE is more positive if there's a greater flux of CO2 into the atmosphere. And this is usually due to an increase in respiration, such as plant respiration or soil respiration. The productivity of an ecosystem also changes throughout the succession of an ecosystem, or after the time since the most recent disturbance event. Productivity tends to be highest during the midpoint of succession, when plants are actively growing and accumulating biomass. Productivity tends to be low in the beginning of succession, when there are not yet many plants on the landscape. And it also tends to be low at the end point of succession, when the community has reached peak biomass that the area can support. When community reaches peak biomass, no new biomass is accumulating, so inputs and losses of carbon tend to cancel out. But we'll revisit this when we look at accumulation of soil carbon in the next video. Take a few minutes to think about each of these scenarios. What are we measuring? Are we measuring gross primary production, net primary production, or net ecosystem production? Or several of these when we measure each of the following variables: net growth of marsh grasses over a season, average CO2 uptake of grasses in a marsh using one of those gas exchange analyzers, the net change in CO2 over a reconstructed wetland using an eddy flux tower, or difference in oxygen production between light and dark bottle incubations. Finally, consider the following scenario. Imagine that an ecologist uses eddy flux towers to measure consumption and production of CO2 in a constructed wetland over the course of 1 year. At the end of that year, he finds that this wetland has a positive NEP, or a negative NEE. He concludes that this wetland should be considered a net sink for CO2. Is his conclusion justified? And why or why not? I encourage you to use the weekly question forum to think through these scenarios with your classmates. We can also discuss them when we meet in the field this week. Your weekly assignment will ask you to try some of the calculations for GPP, NPP, and plant respiration using field measurements. When you have given some thought to these scenarios, take a look at the next lecture video where we will discuss fates of organic carbon.